Hey, good morning. Today we will cover the remaining concepts of the diode before we get into diode circuits next week, right? So different diode circuit analyses, techniques, load line analysis, and then later on next week we'll look at circuits like clippers, clampers created with diodes. But today let's wrap up the diode concepts. So we stopped right before the slide, where we did the example problem. So these are the typical diode IV characteristics or VI characteristics: voltage, current, current, voltage. This is the forward bias or diode forward characteristics. And this here shows near the origin, but these here are the reverse. So they are zoomed in near the origin. This would be forward bias. This would be the reverse characteristics right there. Now, we learned about phi j, right? Phi j is the junction potential that arises due to the diffusion of electrons and holes from the p and n-type semiconductor material. So they cross over the junction, it results in a current, and it results in an electric field. That electric field gives rise to a junction potential known as phi j. That phi j, also known as the built-in potential, no external energy required, has to be overcome if we want the diode to conduct current. And that is a material property, and that voltage is known as the turn-on voltage. It is also referred to by many other terms, such as threshold voltage. I've also heard the term or read the term knee voltage. In our book, for our class, we'll refer to it as the diode turn-on voltage. Sometimes it's also referred to as the diode voltage. Okay, but then the context needs to be taken into account. Diode voltage in general is simply the voltage across the diode, but sometimes the turn-on voltage is also referred to as a diode voltage. But anytime you see the turn-on voltage, that's what they're referring to. For silicon, that turn-on voltage is 0.6 to 0.7 volts. For germanium, it is 0.2 to 0.3 volts. Gallium arsenide, a compound semiconductor, is about 1.2 volts. Okay. So if you have a LED, the LED is not going to turn on unless you're supplying at least 1.2 volts. So the knee voltage, of course, I mean, sorry, not this turn-on voltage, of course, is the potential that is required to overcome the junction potential, phi j. Until then, we see that the current is almost equal to zero. It's not quite zero. There is still a small amount of current that is present. Okay, there is a small amount of current that is present. We have the minority carriers that are crossing the junction. So if we zoom into the origin, we can see that right here. And when you did the PSpice simulation, if you plotted the diode current on the log scale, you would have been able to see something like this that went through the origin. If this ID was in the log scale, okay? Because the log scale will allow you to zoom into 10 raised to minus 14, 10 raised to minus 15 values, okay? So that was the point. Also, in the reverse bias, we have a small current that is flowing due to the minority carriers again, and that current is known as IS, which is the saturation current, IS. Now, IS is present in both the forward and the reverse characteristic, but typically we refer to it as reverse saturation current, more commonly saturation current, IS. And it's an important part of the diode equation that we will see in the next few slides. Now, in the reverse bias, we know that the well, actually, let me wait. If I get the next slide, yes. Gallium arsenide, GaAs. So let's gallium arsenide, GaAs. These are the three most common semiconductors that we deal with. There's of course gallium phosphide, gallium nitride. Gallium nitride is really big right now in the market, right? You have these fast chargers using gallium nitride material. So it has specific properties that are useful. This is the diode equation. This is one of the most fundamental equations, and there is a typo in there. There should be Q charge in there. Okay. This diode equation is also known as the Shockley equation. For some reason, Jaeger, the author of our book, doesn't refer to this diode equation as the Shockley equation. But if you read some other books which they refer to Shockley equation, this is what they're referring to. Okay, this is the most fundamental of diode equations. There are multiple quantities in here, right? Remember back to first week in the first day of class, I made a statement about how we can describe a quantity or a person by like maybe one word or one variable. But if you have more words, more variables, you're fully able to describe that quantity. And so here in the same case, if you're trying to describe a diode current, there are approximations, there are multiple variables that we can use. In this equation, we use IS, saturation current. Let me slow down and write better. Q is, of course, the charge, standard unit charge. VD is the diode voltage. T is the temperature in Kelvin. And let's see, N is non-ideality factor. For the most part, for most silicon diodes that are used in most common applications, this non-ideality factor is taken as 1. Okay, taken as 1. Oh, and of course, K is the Boltzmann's constant. So temperature would be a constant. Boltzmann, K is a constant. You have Q is a constant. The only difference or the variable would be VD. We can reduce this further because we know that the thermal temperature or the thermal voltage is KT over Q. And because this allows us to reduce, actually, and so then this can be written simply as ID is equal to IS times E raised to VD over VT. E raised to VD VT minus 1. Okay, The Q over KT is 1 over VD. 1 over VT, thermal voltage, and N is typically 1. And so the equation can be simplified to simply the saturation current times E raised to VD over VT. So this is one mathematical model that describes the diode current and the diode voltage in terms of the diode voltage. Now, if you take a look at all three of these, there's zero bias, reverse bias, forward bias. In zero bias, we already saw what happens, right? Zero bias is when we first bring, let me go back to that slide right here. When we first bring the P and N type semiconductor together, there's no external energy. We are not applying a bias, right? And so simply P and N junction coming together. And so we already know what happens at zero bias. So a diode under zero bias reaches an equilibrium position, thermal equilibrium. There is no external energy that is being applied. Net flow of charge is equal to 0 because of the competing mechanisms of the drift and the diffusion current, right? So it reaches an equilibrium position. Net charge is 0, hence current is 0. And of course, results in the junction potential phi j. Okay, results in the junction potential phi j. And this is typical semiconductor behavior. It doesn't matter what semiconductor material you use. If you have a p-type and an n-type semiconductor material together, you form a p-n junction diode. Sorry, you form a p-n junction. Then these effects do occur at that junction. So under zero bias, there's an equilibrium state. Okay. So then what happens if we apply a voltage, an external energy source, one in the reverse bias and the other in the forward bias? So what is reverse bias, first of all? Reverse bias would be, actually, let's do this. Okay, so this is P and this is N. Positive, negative, right? Let's just use those terms. Now, if you connect an external source with a negative end connected to P-type and the positive end connected to N-type, we say that the junction is now reverse bias, or the diode is now reverse bias. Here, this is the depletion region. And you have, of course, excess of holes on this side and electrons on this side as the majority carriers. But right near the depletion region, the space charge region, we have ionized donor atoms and ionized acceptor atoms. So when you have the negative end of the voltage connected to a p-type material, what do you think would happen in terms of charges? That would be the result, yes. So negative charges, positive charges. Opposite is attract, right? So the holes are pulled towards the terminals and the electrons are pulled towards the other terminal. And so then it results in depletion region being increasing or the depletion region width increases. There is still minority carriers that are crossing the junction. That is always going to be true. Okay. And so IS, the saturation current, is always present. Okay. Minority carriers will be going through. Minority carriers, again, as a reminder, in the P-type material, the electrons are the minority carrier. And in the N-type material, holes are the minority carrier. And so again, that would be opposite charges attracting. Okay, so the depletion region increases, it widens, meaning it's now somewhere like this. And hence we don't have any significant current flow when it's reverse bias. Okay, let's take a 10-second pause. Write it down, think over it. Let me know if you have any questions. Yes. Yes. In circuits 2 and 3, you'll. Oh, in a lab, you had a diode. Yes. Okay. That would be the ideal diode model. So ideal diode model, basically you just, we take the X and Y axis and we say positive X, diode is on, negative X, diode is off. So that's the ideal diode model. We simply have two states, on and off. And then there is a extension of the ideal diode model where we say, okay, diode is on, but it requires about 0.6 or 0.7 volts battery to turn on. And so we put a battery or a voltage source in front of the diode. So again, there are various different models. Ideal diode model is very useful when we want to do like a quick analysis of a circuit, right? You have multiple diodes in a circuit, and we have, like, let's say, multiple sources in the circuit. We simply just model the diodes as they're either on or they're off, and we analyze the circuit and determine the voltages and currents. And so it's very useful in certain scenarios. No, there are multiple different models. So as I stated in the beginning of this course, there's no single model that will work for every single circuit. It just depends on our needs. If we just have a simple circuit and we need, as you said, in circuits 2, you performed an analysis where you had a diode and you use the ideal diode model, whether a diode is on and off. And that is very useful when you wish to perform that kind of analysis. That is also actually something that a multimeter would do, right? You want to test a diode, you plug it into a multimeter. Multimeter would tell you, applies about small amount of current and the voltage. If the diode turns on in one direction, it'll tell you, okay, yeah, this might be forward bias. Diode should be off in the other direction. If it's on in both directions, or it's off in both directions, then something's wrong. That's where you just want to know whether it's on or off. Make sense? Yeah. So let's see. Oh yeah. So in the depletion region widens, and we still have minority carriers that are flowing through. So we have a reverse saturation current. Okay. So there is a saturation current that is present. It's present in forward bias and in reverse bias. Typically, not typically, it can be referred to as reverse saturation current, or it could be referred to as simply saturation current. One thing to note, if you increase the voltage in the reverse bias, the saturation current will increase because it's generating more carriers now. The electric field is increasing, it's imparting more energy to the minority carriers. So even though the name is saturation current, it does not really saturate at a level. And you can simulate this in PSpice. In reverse bias, the first circuit, the simple circuit with a single diode and a single resistor, you can simulate from -1 to +1 volt. Then you increase -2 to -2 to +1, -3 to +1, -4 to +1, -5 to +1. It'll keep on increasing. The reverse saturation current will go from 1 picoamps to 2 picoamps to 3 to 4 to 5. And you can actually simulate that. So the reverse saturation current does not actually saturate. Okay, then comes forward bias. Now, in forward bias, let me use the same. Let me use the same image right here. And the only thing you change is this. Now, we are going to apply a positive voltage to the p-type material and the negative voltage to the n-type material. And the exact opposite thing will happen. Like charges repel, and so they are now moving towards each other. Minority carriers are still have the same forces of attraction. So minority carriers will still have the same flow of current. And that's why we have IS both in the forward and the reverse bias. But now the holes and electrons will have enough energy to actually overcome the junction barrier or the junction potential. And because that happens, electrons and holes will start flowing freely across the junction. And you have current flow to the material. So current flow. That would be the direction of the current flow. Okay. Same as the vacuum tube diode. A vacuum tube diode, we have the electrons flowing from the cathode to the anode. We have the same thing here. Electrons are going from the n-type material to the p-type material. And current flow is marked as flowing from the anode to the cathode. Okay. Let's write down ID. And this would be VD. Now voltage. And once current starts flowing, a very small increase in voltage would result in a very large, this is zoomed in and magnified. The point is a very small increase in voltage would result in a large increase in current. Okay. Of course, that is also known as the forward current, just because it's going in the forward direction. When we are writing out equations, we refer to the negative, we refer to the reverse bias voltages and the reverse bias currents with a negative sign. Okay. Otherwise, our equations would never balance out. So we refer to the reverse bias conditions with a negative sign. Okay. All right. Any questions? Yes.
So if I apply a high amount of voltage and a depletion zone of reverse bias, at what point will it just tear apart?
Good question. That would be our breakdown. So diode breakdown conditions when we will look at that. Yeah. So it's like question being asked was about a high enough voltage in the reverse bias, what would happen? Yes. Anode and cathode. Good question. Anode and cathode. These are naming conventions that were used for the vacuum tube electronic devices. I'm not sure why K was chosen. Maybe because it's pronounced as K and not C. And probably C is referred, it's reserved for coulombs, for capacitance. Yes. On your left, right there, going on the back. We got Spider-Man. Yes, you had a question? Okay. All right. You want me to wait on this slide then? No, no, it's fine. We can. I'll, I'll synchronize. Which ones were those? VT was what, 25 point something? 20. I'll take a look again. No, Q is always 19. Did I give 14 in the class? I don't think so. Okay. Yeah, now Q is the standard single charge of a particle. So either an electron or a hole would have 1.6 10 raised to minus 19. But I'll take a look about the thermal volt. Can you send me an email so I can look back in the homework? Unless the question specifically states, it typically is just 25.8 millivolts thermal voltage. But definitely send me an email about that. Okay. All right. Thanks. All right. So we'll see how the diode current equation reduces in all three conditions. So in zero bias, we are not applying any voltage, right? The only thing left is the thermal voltage. And so it just becomes the entire term right here simply reduces to 1. Right? E raised to 0. So it reduces to 1. And so mathematically, you can say, yeah, for zero bias, we have 0 amps of current flowing through, which makes sense. You're not applying any voltage. You would not expect any current. In reverse bias, now you're applying a negative voltage. You apply a negative voltage, you get negative saturation current. It's a minus IS. Okay. So for zero bias, output is 0. For reverse bias is saturation current and negative minus IS. And then forward bias is where we actually perform our calculations. And so even in forward bias, it simply reduces to e raised to VD over VT. That is because whatever voltage we apply across the diode, VD, this term 1 is probably far less than this term right here. And so we can state that ID is approximately equal to IS times e raised to VD over VT. Okay. And N, of course, is the non-ideality factor. Almost all conditions, normal applications, normal diodes, N is always 1. Okay. Yes. 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 Yep. That's what we did. So the question being asked is, can we simplify the equation, diode equation? And so, yeah, simply VD over VT. And that is also sometimes a personal preference. If I'm working with an equation and I have too many terms in there, sometimes I like to look at, let me get rid of this equation, make an approximate answer and see how it works out. So as a working engineer, you would have to make certain compromises and certain decisions that way too. You would assume certain conditions and try to solve your circuits. Okay, so from the diode current equation, we can write an equation for the diode voltage. VD would be VT log of ID over IS plus 1. You're simply rearranging the terms. So we take it become ID over IS, right? So that's what we have here. And then ID over IS, you take the 1 on this side, so it becomes +1. And then we get rid of the exponent by taking the log of the whole thing. Okay, so you're simply rearranging the terms of the current equation to obtain the diode voltage equation. Okay, and when we solve for the derivative of the diode voltage with respect to the temperature, the thermal voltage, we get a very linear relationship and a fixed value of minus 1.82 millivolts per Kelvin. Okay, and this is highly linear. This is highly linear. So the diode voltage changes as a function of temperature. Okay, and that is what we simulated in procedure 3. Procedure 3 of the lab of the diode P-SPICE simulation. Procedure 3 was not in the lab manual. We were trying to simulate what the diode voltage would be as a function of temperature. And for the most part, it's very linear. And so in the book, there is a very neat example of a real life application. You take diodes and you can build a circuit around it where you can translate the change in temperature and you can create a thermometer. So most digital thermometers actually use diodes. And again, the reason is because this change right here is very linear and very constant. Okay, so definitely read the example on this application. I'll probably assign it as a reading assignment. Okay, digital thermometers. Okay, so in reverse bias, we're going to look a bit more in depth because one of our diodes, one of our topics is the Zener diode, very important. Okay, and that works in the reverse bias. So in the reverse bias, we talked about how the depletion region increases. Let's look at a little bit of the electrostatics, right? Because the reverse bias attracts the carriers away from the junction. That's the reason the depletion region width increases, right? So what is actually happening is right here. And that's the increase. And the increase happens, of course, because the carriers are attracted away from the junction, which increases the electric field. The electric field is now increased on both sides of the junction, right? The carriers are going away. So now you have more ionized atoms on either side, right? On either side of the junction. And that also increases because the electric field increased. It also now increased the junction potential. You need more voltage to overcome that depletion region width, right? So reverse bias, simply stated, depletion region width increases, that increases everything. And VR is, of course, the reverse bias voltage that is applied to that PN junction diode. Okay. So it increases the built-in potential. Built-in potential is now phi j plus VR. And VR is the reverse bias voltage that is actually applied, the external energy source. So there are no majority carriers that are crossing the junction. We have no major current flow, but the minority carriers are still crossing the junction, resulting in that reverse saturation current. If we keep increasing the voltage, the saturation current keeps increasing. Okay. However, that doesn't take place indefinitely. At one point, a breakdown of the junction occurs and a huge amount of carriers now cross over. They're now crossing over in the reverse direction, which is indicated right here. So for a long time, the current is approximately equal to simply IS or negative IS, as close to zero as possible. The the saturation current is in the order of like picoamps and femtoamps, very, very small. But after one particular voltage or one particular threshold in the reverse bias region, a breakdown of the junction occurs and a huge amount of carriers just cross over in the opposite direction. And that mechanism by which the breakdown occurs is known as Zener and avalanche. There is actually two kinds of mechanisms, okay? So Zener is one and avalanche is the other, okay? Let's talk about avalanche first. What happens in avalanches, in reverse bias, right? We already talked about how. Let me paste that diagram again. In reverse bias, we are applying negative, let's see. We are applying negative voltage, negative end of the voltage to the p-type material. And so it's attracting the holes, and the other side, it's attracting the electrons. So the depletion region is increasing. Now, when more and more energy is imparted due to the external energy source, these carriers have now more energy. They are in a rush. And remember, this is a very small junction with a large number of atoms. So a large number of carriers are present. And what happens is they run into other electrons and other holes, and they run and collide with the other atoms. And they're knocking the atoms out of the lattice structure. And when that happens, it knocks off more electrons and creates more holes. So it's like a cascading effect, hence the term avalanche. And so at this particular point, from the external energy source, from the external voltage that we apply, there is so much energy that is imparted to the carriers that the carriers are now moving freely in the material. They collide with other atoms and other particles in there, creating a cascading effect where there are a whole lot more free charge carriers available to move. And at that point, they now have sufficient energy and sufficient numbers to simply move through the junction and in the circuit. And because of the cascading effect, because of the avalanche effect, it is referred to as the avalanche. It also is referred to as the impact ionization phenomenon. Okay, impact ionization. One particle collides with another atom, releases more particles. They in turn would collide with other particles and other atoms. And then it just causes an avalanche of free carriers. And because of the free carriers, at that point, a huge amount of current results. And so this is exaggerated. This is exaggerated, okay, just to show a slight slope. But in real life, 1G or 2Gs exaggerated? 2Gs, right? I made a hash of this. Exaggerated, yes, 2Gs. It's been a while since I've written out that term. The slope is exaggerated, okay? Typically, that reverse bias voltage is held pretty much constant. And that brings me to the second, well, actually the first phenomenon of Zener. The Zener effect is observed in diodes which are very heavily doped. Okay, really heavily doped diodes will have a very thin, heavily doped diodes will have a very thin depletion region width. And because of the very thin depletion region width, the charge carriers are able to cross over in the reverse direction. And this effect usually occurs about less than 5.5 volts. 5.5 to 5.6 volts. So it only occurs when the voltage is about 5.6 volts or less. But in general, it has come to be accepted that all reverse action is now referred to as Zener diode. So even if the diode, it's more than 6 volts or 10 volts, it is using the avalanche effect, but it is still referred to as the Zener effect. Okay, so there are two mechanisms, Zener and avalanche. Zener is typically in heavily doped P and N-type semiconductors, and it occurs typically for less than 5.6 volts. And above it is usually the avalanche effect. But in general, it has come to be accepted that everything working in the reverse bias is Zener. Okay. And as I said, this was an exaggerated slope. Typically, the slope is far more like a straight line. So let me draw out a slope. So typically, it would be almost a straight line. Okay. Yes. Not lattice structure breaking down. It's the atoms and particles being knocked off. The avalanche effect. Yes. Diodes will still. The question being asked is, if we are operating a diode in the reverse bias, would it still work in the forward bias? The answer is yes, unless the thermal dissipation is so much that we destroyed it. But again, there are diodes which are specially formulated to work in the reverse bias, which is the Zener diodes. And that is one of the experiments we'll perform in lab 4, I believe. So Zener diodes are specially formulated to work in the reverse bias. In the forward bias, it will work as a normal diode, but in the reverse bias, we are using the Zener effect. Okay. And the reason we use those is because they hold the voltage near constant across its terminals. And so depending on the requirement, engineers can calculate the amount of doping that is required and create Zener diodes to work in the reverse bias for, like, say, 2 volts, 3 volts, 4 volts, 5 volts, going up to like hundreds and thousands of volts. Okay. So you could connect a diode, stick it in the wall in reverse bias, 110 volts, it will still work fine. In fact, the normal diodes that we use, the 1N4000 series, 1N4001, 4002, 4003, it goes up to 4000, well, it goes up to 4009 and beyond, but especially 1N4001 up to 7, 1, 2, 3, 4, 5, 6, 7, they have the exact same characteristic. Okay. The only difference is that the reverse bias PI, we call peak inverse voltage, that each diode is able to handle increases with that number. So 1N4001 can handle up to, I think, 50 or 60 volts in the reverse breakdown before breaking down. And 4007 can handle up to, I believe, 400 volts in reverse bias. So there are, several different applications that you can use in several different diodes that will match those applications. So if in your lab kits, sometimes if the manufacturer the supplier does not have enough of a single type of diode, they will send in other kinds of diodes. So in your lab kits, you have the small diodes. There's a set of 4 black epoxy packaging with a gray band. It could be 4001, it could be 4002, 4005, or 7, would not really matter. The forward characteristic of the diode is exactly the same. It's the reverse voltage capability that is different. All right, other questions? There's one more topic, and we have just enough time to get through. But any questions before we get to it? Okay. So in the reverse bias, we talked about the breakdown. Now there is a now there is a quantity that that we look at is the diode capacitance. Okay, and this is present in both the forward bias and the reverse bias. But let's take a look at the reverse bias first. So what happens? Let me use a illustration. Typically we create semiconductors like this, right? This is the top view. And we create, let's say, not even this big, like a tiny. So this is a N-type wafer. We create a P-type feature inside it, right? So with the top view, you have a layer of N-type material, and you're creating a P-type material on top. And so now, if you visualize it from the top, what do you have? Two parallel plates. One is a P-type, the other is an N-type. Charges accumulate on either side of the depletion region. So if charges are accumulating on different sides of the depletion region, it forms a capacitance. And we look at the capacitance of both forward bias and reverse bias. So this is the top view. This is, well, for lack of a better word, let's just say the side view. But a 3D illustration would look something like this. Let's see. And then you have, actually, so this is our N-type. And let me do a cross section right here. So this is my P-type that is embedded inside. And right here is my junction. Coming from the top, coming from the bottom. The depletion region, the width of the depletion region is basically the distance between the two plates. Okay, so the capacitance between the two plates would be given by the cross-sectional area, the physical dimensions of the implant, right? And that would basically be the areas where the P and N-type material are overlapping, right? Two overlapping plates is the cross-sectional area of the overlap. So C would be standard capacitance formula, epsilon A over D, right? So in this case, the capacitance, let's say for silicon, would be epsilon S. A is the cross-section area of the overlap of the p-n junction. And then D would be WD0, the width of the depletion region. Make sense? And because there is charge accumulating on both sides due to the applied voltage, it has capacitance. In case you need to remember, circuits 2, I believe. Q is equal to CV. So capacitance is Q over V. Capacitance is basically the capacity of that element to store charge as a function of the applied voltage. How much charge you can store, how much Q is present due to the applied voltage V. So in this case, our applied voltage is the reverse voltage VR, reverse voltage, and phi j is our original junction potential. And so we can describe the equation in the reverse bias. It is known as the junction capacitance. It is also referred to as transition capacitance. So if you look at a different book or a different author, you might see the word transition capacitance. They are both referring to the capacitance that is present in the reverse bias. Okay. The forward bias capacitance is known as diffusion capacitance. In reality, diffusion capacitance and the junction capacitance are present in both reverse bias and in the forward bias. It is just that the effect of either one is quite small or diminished, one for reverse and one for forward. So in reverse bias, the effect of the junction capacitance is magnitudes higher than the diffusion capacitance. So we simply refer to junction capacitance in reverse bias and diffusion in forward bias. In forward bias, the equation can be described as the forward current ID times T or tau T, and that is the transit time. And transit time is basically the minority carrier transit time. Minority carrier means either electron or hole. If there's an empty spot, remember, electron moves out, creates an empty spot. So the reverse also occurs. Electron can move into an empty spot. That process is known as recombination. So it's known as the minority carrier lifetime. Okay, so it's a transit time, minority carrier lifetime. How long before that electron will fill up a hole? It's typically 10 raised to minus 15 seconds. Okay, femtoseconds or smaller. Anyway, so CJ0 is basically what I wrote out here on the right, epsilon S times A over WD0. Okay. Your book rearranges, the book rearranges the terms a little bit differently, but it's the exact same equation. But I hope the physical concept makes sense. Okay. All right, we're going to end class here today. Quiz on Monday as usual, based on the work you have done this week. There will be one more homework over the weekend, and then quiz on Monday. Okay. We'll end class here today, and I'll see you all on Monday. If you have any questions, we still have 10 minutes before the next class.